Hello, everybody. I am Mr. Auerbach, and I am here to talk to you about the electromagnetic spectrum, atomic emission spectra, and the Bohr model of the atom. Okay, so this is basically the third section of the particle nature of matter. It's about atomic emission spectra and the Bohr model. And so, what are atomic emission spectra? Well, it looks like this, right? This is on the top, you have a picture of a prism, and that prism splits light into its various wavelengths. Wavelengths are different, in this case, visible wavelength, different colors of light. And as you can see, we have different wavelengths. The violet light has a shorter distance between the peaks or the troughs of the energy of the photon is what a piece of light energy is called, whereas the red has longer distance between it and therefore has a longer wavelength. Visible light is a mixture of all of those, and what's happening here in this picture is that the sunlight is being split into its different wavelengths, and we call that a continuous spectrum because the sun uh, has what we call continuous spectrum light. But down below it, we see a lamp made of just hydrogen. And what we see is that when it goes through the prism and splits into its different wavelengths, we only see four lines. We see a violet light, a blue light, a sort of teal light, and an orange light. And every hydrogen sample in the universe will produce that light. That's one of the things. We call it a spectral fingerprint. Um, and every element has its own fingerprints. So hydrogen on Earth is going to be the same as hydrogen on Pluto, is going to be the same as hydrogen, in the middle of the universe somewhere. And so, moving on, what is this? This is what I mean here. You can see that every element that they show here. I'm not going to give the answer to this, but there's an unknown here, and the idea is which one of these elements does it match? It's an identical match for one of them, and so if you saw that element somewhere in looking out at the universe, out at the solar system or something like that, you would know that that element was present because you can see the fingerprint. Not so bad, not too bad. The thing comes from the question is where does that light, where do those bright lines come from? And turns out that a fella named Niels Bohr figured this out. And I'm using the book as a point of reference, by the way, because this is what you need to be looking at anyway. And so this is kind of a walking guide through it. So the it turns out the short story is that the short story is that light in these spectra comes from uh, atoms that move. We're having technical difficulties. Sorry, I tried to do something on the screen and it didn't work. We're just going to pretend it didn't happen. Anyway, you have your model of the atom. And let's move forward a page because this is what we're talking about here, right? You've got the nucleus of the atom, and then you have electrons going around at different energy levels from the nucleus. And so this first one's level 1, level 2, and level 3. And what level an electron is on depends on how much energy it has. So the electrons on level 1 have less energy than the electrons on level 2. And if number 1 wanted to go to level 2, it would need more energy. And that ultimately is what they're talking about here. So what we see here in this diagram of these three bits, let me see if I can make this thing work. Here's the pen. Anyway, I'll see what I can do with this. So you have in this set of three pictures, you have got a sequence of events. One, sorry about this, First time with my new toy here. 2, and then finally 3. And what happens at first here is that an electron absorbs a photon of light. And what you'll notice then is it knocks that electron up to a higher level here. And it's kind of like no, it's kind of like this. Right? You are putting energy into the system. That photon of light adds energy to the system, and just like smashing that the high bell game with a hammer causes the weight to go up, hitting an atom with light, certain kinds of light will cause the electron to go up. Here's a GIF of it that I found. Right, so you've got an electron going around, and you can see it's on the first level and it absorbs a photon there. And after it absorbs a photon, it goes to the second level. Here, let's watch it again, because then when it drops back down to the first level, you see what says emissions. You have absorption there going up a level. And then when it drops back down, it releases that energy. Just like, when you hit the high bell game, the weight goes up and the weight has to come back down and it releases that energy it absorbed. Well, it's the same thing, except it's with light. Atoms absorb photons of light, and after they absorb the photon of light, it drives the electrons up to another level, and when the electrons drop back down to their original level, they release that line. And every element has a different number of electrons in kind of different arrangements. They all have different numbers of electrons, every single element, and every single element has its own distinctive spectrum because that's because of the interplay of all the different electrons going up, different numbers of levels, coming back down. Some electrons absorb certain types of wavelengths and not others. Some atoms absorb certain wavelengths and not others. Other elements absorb different wavelengths than those, and that's how it goes. And that is how we get our continuous spectra. Um, just one more word about this little diagram here that's on the third page. This has to do with the energy levels between the atoms. And so the energy is called quantized because it is either going to be uh, here or it's going to be here. There is no in between with atoms. It's called quantization, meaning either this quantity or that quantity, nothing in the middle. So what they're saying with this picture is that uh, unlike a ramp where with continuous energy, where a person could just walk up the ramp, take small steps, in quantized energy, it's specific amounts of energy go up, cause electrons to go up specific amounts, just like stepping on stairs. You go up, there's only one amount you can go up when you're on a stairway, and that's one step. There's no going up a quarter of a step or three-quarters of a step, right? Either one or none. And that's the way it is with quantized electron energy in the Bohr model of the atom. Thank you very much for your time. I am Mr. Auerbach.